There we go. Yes, it is, madam. It is in progress. And I got it. Very good. So, welcome everybody to TennaTalk, a journey of discovery about all things antenna. Tonight, TennaTalk will be doing a Q&A session, podcast number 6, antenna modeling with Easy Neck and Sim Smith. And of course, TennaTalk is a production of the Antenna Whisperer, Rudy Wiedemann, K7RAW, supported and sponsored by LVRAC, the Las Vegas Radio Amateur Club here in Las Vegas. And on that note, I'm going to go ahead and turn it over to K7RAW. I'll stop my screen for you, Rudy, and go ahead and take it. I will put you on spotlight so everybody will start to just see you coming up. And if everybody knows how to use the view caption on Zoom, you can either have it up on the top or on the right-hand side, however you want to do it. So Rudy, the floor is yours.
That's a scary thought, Charlie. Thanks so much. Good evening. Hey, guys. Good evening. Good evening, David. Good evening, Steve.
Good evening.
Hey. So I suspect we may get a couple more stragglers coming in here late because of the holiday weekend. But hey, let's get going anyway. So I got some feedback the other day on the Thunderbird net that the material was a little bit dense. But you know, I kind of designed it that way because I want it to be a little bit of a stretch. Okay, if you're not stretching, okay, you're probably not growing. So you need to stretch a little bit. But that's why we do the Q&As, is to help clarify and answer questions and defuzzificate things and demystify. So at this point, I've got Sim Smith and Easy Neck up and running on the other screen. So I'm going to open it up to questions, clarification questions, anything fuzzy, whatever you guys want to learn more about regarding the Easy Neck and Sim Smith and how those things work and how they come together. Hey, there's Ron. I told you Ron would be here.
Speak of the devil, there he comes. And he's connecting to audio, so it's going to just take him a second.
Don't everybody yell at once.
Yeah, Ron, Rudy.
Yeah.
I got just a simple question. It's related, of course. Like, I know the far field, there was a question either on the general or extra exam, and I just memorized the answer, and I didn't understand any of it. You know,
okay.
The far field, the way I thought I understood it is like when a radio wave takes off from an antenna, you know, some goes in the air, some goes down onto the ground and reflects up. And then it's a question when those two combined, are they in phase or out of phase? And that sort of determines the radiation pattern. But could you sort of elaborate what you mean by far field a little bit?
You bet. I'll be happy to, Steve. That's a very great question because a lot of people don't understand it. It's actually in the world of physics, radio waves, optics, X-rays, gamma rays, any electromagnetic radiation. There's the near field and the far field, and you might see it referred to as the Fraunhofer region and the Fresnel region. Fresnel, like those funny flat lenses. Yes, same dude. Anyway, the way to think about it is an antenna, for the most part, can be looked at as a collection of little segments of current, of RF current, okay? And each one of those can look like it's radiating on its own, almost like if you took a line of pinholes in a sheet of paper and you shine a laser light, a uniform laser light on the back of those. On the back side, they would interfere with each other, but only at a distance would you get a wave and you'd get an interference pattern, okay? But if you're right up close to them, you'll see just the holes, okay? That's the near field. If you're in the far enough away, they combine. And once they combine to create a more stable pattern, that's the far field or the Fresnel field. And that's generally what you need to measure when antenna people are out on the range measuring the antenna. They want to measure it at the far field, which is at least a few wavelengths away. Yeah. Does that make sense?
Yeah, I sort of understood it that way, but you
Great.
clarified it, so good, thank you. I have some more, but I'll wait for other people. Ron
Okay.
must have some questions or.
Hello, Ron. Good evening.
Hi there, Rudy. I got a question.
Yeah, go.
When you're using EasyNet, is there some rule of thumb that you use to determine how many segments you break your wire into?
Yeah, there kind of is. Couple of guidelines. Number one, you need to have, if whenever you're going to have an intersection of, let's say, a ground plane wire and a vertical wire, okay,
Okay.
then you want to do that at an intersection of two segments, okay?
Mhm.
It's going to complain if you have a one segment vertical and you try to put a ground plane at the end of that, it's going to complain because it says, hey, I don't have an end of a segment here. So that's the first thing. The second thing is for its calculation engine, it cannot handle segments that are all that long. So if you got long elements, you want to break it up, and it'll actually tell you there's a little window that'll pop up saying your segments are too long, recommend such and such, no longer than that. And you do a little math and you just add some more segments to that wire or to the appropriate wires, and the little complaint window goes away and you're off and running. So those are a couple guidelines that I use.
Okay, thank you.
You bet.
Rudy, when you say segments, are you talking about multiple ground radials, for example? If you don't show it, oh, okay. Can you explain that a little better?
Okay,
me?
so let's talk about a dipole. The easiest way to make a dipole is what I did in the video. Take a single wire, horizontal, up at so many feet up in the air, and put a source in the middle. And if I gave it one segment, that wire was one segment. But if I want to put that, for example, if I want to put put the source as an off-center fed, or worse yet, an end fed, okay, with a very short a short counterpoise on it, for example. Make most of it an end fed half wave with a short counterpoise out of a single wire. I can do that, but then I have to make a bunch of segments. Typically, the counterpoise is going to be about 5% of the overall length. So I have to have at least 20 segments. And my rule of thumb is I like to always have an odd number of segments. Why? That puts one of those segments always at the center of that particular element, that wire element, whether it's a ground line, a vertical, whatever that case may be. It always gives me a nice symmetric balance where I can put a source right in the middle of that element.
Okay.
Is there any problem with adding too many segments?
It slows the calculations down. I just put up enough segments so it stops complaining. It'll tell you, it says your segment length is 6 feet, recommend less than 2 feet. So you add 3 times as many segments and you're 3 or 4 times as many and you're generally okay.
Okay, thank
But
you.
I like to have odd number segments.
Is there any rule of thumb in terms of, let's say, a half-wave dipole? How many segments would you use on a half-wave dipole, for instance?
It depends on the length. EasyNet calculator goes by number of feet per segment when it's happy.
Okay.
It doesn't
Yeah.
want to have physical segment lengths in feet that are very long. It's only, think of a few feet per segment. That's a good guideline. 2 to 3
Yeah.
feet per segment, and you'll be right at least half the time. If not, it'll complain and just give it a few more segments.
Okay, so whether you're doing an 80-meter dipole or a 20-meter dipole, you'll have different number of segments then, apparently. Yeah.
Yeah.
Okay. Okay.
Exactly.
Yeah. Okay.
Cool. What else?
One thing I didn't see in there, but I thought I've read in other places, let's say, especially if you're dealing with a vertical antenna, the ground conductivity. Is there something in EasyNet? I didn't see that, but I didn't look at it. I haven't
Yeah.
downloaded like you said I should have done, but is there something when you're looking at a vertical, if you can specify, like out here, the ground conductivity would be very poor and other parts of the country would be very good. But is that something that was in the program that you showed there?
Yes, sir, it certainly is. Hang on a second, I'll show you. Okay, can you guys see my screen?
Yep.
Yes.
Yeah.
Okay, so this is Sim Smith. Let me switch this over to EasyNick. All right, so we got EasyNick on top. By the way, does anybody know what this is?
Center antenna image.
Let me zoom in for you, see if you can figure it out.
It's a coil.
Oh,
It's a noodle antenna.
making me hungry.
This is my 10-meter noodle antenna that I modeled. Okay, so let's if we go to ground type, okay? Ground description and ground type right over here. I can say it's free space, perfect, or a real ground, either high accuracy or what's called mini neck. Now, be perfectly honest, I haven't really dug into the difference between the two. I just use the default for the most part, unless I've got an elevated radial, in which case this doesn't really apply. But if I'm actually connecting the ground to the ground, or if another thing, if you start your antenna at 0 Z elevation, it's going to assume that that end of the antenna is connected to the ground, and it's going to complain about it because it's going to say, hey, you got a feed point here, you're grounding that thing. So then let's see, ground description. All right. So Siemens per meter. So you've got basically conductivity here. And hang on a second. Let me bring it up. That's what it brought up. You can put in the conductivity that you want, dielectric constant. So you can really get tricky in terms of what kind of ground you want to define. That's kind of an advanced subject, and I would suggest that you take a look at the EasyNet documentation for that. But that's generally what the ground means, is ground type.
Because everything I read says, like a vertical antenna, especially, is affected by the ground conductivity, quite a bit. So it's nice when you're testing out a vertical if you can see, if the ground is good or bad or whatever, of course.
Exactly. Okay. What else?
Rudy, when you're using using an unknown, like a
Yes.
auto transformer.
Uh-huh.
Now I'm assuming that's going to be wound on a toroid.
Yes.
Okay. Is there any rule of thumb for the size of toroid that you need, depending on what kind of power you're going to be transmitting?
That's a great question, Ron. So basically, an FT240-43, which is a mix 43 with an OD of 2.4 inches, is what you really want to use for ununs and balance. Not for common mode choke. You use a mix 31 for common mode choke of the same size. Then what I would do is, I don't have it here right now, but I wound one the other day. If you're using a good solid copper winding wire, like a magnet wire, I think it's 14 gauge. It's either 14 or 16 gauge. I think it's 14 gauge. And wrap it really, really tight. I can get a lot of turns on there. And that will handle well over 100 watts. So you're very safe at 100 watts for that type of device. It will not oversaturate. It will not overheat. It will be very effective to comfortably over 100 watts, probably 120, 130, maybe 150 watts easily. Now, there are smaller toroids, FT 115s, FT 130s, FT 98s, 68s, 80s that are proportionally smaller, and everything's in inches. So 68 is 0.68 inches outer diameter. And they wind those typically with a lighter wire, like maybe an 18 gauge wire, solid copper wire. Those probably are good for 25, 30 watts. but you know, it so much depends on the band. These things, if you wind them properly and you've got enough turns on it, if you're using very small fraction of the toroid, it'll actually get hotter because the energy is concentrated. Whereas if you use more base turns for your ratio, so if you want to build a, let's say, a 49-to-1 anan, okay, and you use 21 turns and on your secondary and 3 turns on your primary. That's a ratio of 7. 7 squared is 49. So the impedance ratio is 49, as we all know by now. So it's better to do that than to say do 14 and 2. If you do 14 and 2 and you've only covered half of your toroid, then you're not spreading the heat out and the magnetic field out as uniformly around that toroid, and you'll get hot spots. You'll get hot spots around the coil. So there's a few tips on coil winding.
Now, I think you mentioned earlier too that you could actually double up on toroids for
Yes,
more
you
power.
can. Yes, you absolutely can. You can sandwich 2 or even 3 of them together and wind them together in a single coil.
Gotcha. Thank you.
And then you can go to 200-300 watts of power for those people who have small linears.
And then also, like I know with Robert at the last time we were out at the park, he just had a toroid wound and it was all on the outside. Now, other times you see commercial units where they put it in a box, but is it better to leave it outside so that the heat can dissipate better, or how much of a difference does that make? Where it looks nice, maybe we put everything in a nice little plastic box or whatever, but is it better to leave it outside let's say if you're running 100 watts and you don't want to push it too hard, is it better just to wind the toroid and have it on the outside rather than put it in a box, or does it really make that much of a difference?
If you're winding it with magnet wire and you've selected the appropriate size wire, then you're going to minimize the amount of ohmic losses or resistance heating that you get there. And if you've selected the correct size toroid for the kind of power you want to work, then you're not going to heat up the toroid very much at all. So the answer is, from the box's thermal point of view, not really that big a deal. You can put it in the box under those conditions. The advantage of a box is you can mount and seal the coax connectors very nicely onto that and kind of keep your connections out of the weather. That's definitely an advantage. But if you're going to do it on a POTA activation, and you're not standing there in the rain, then you can do what I do. I just solder on a connector right onto the input of the wires. And if we get into this a little bit more, I can actually show you some of these anans and chokes that I've built. But let's get back to the topic of the evening and make sure that everybody's got their questions answered on SimSmith and EasyNeck before, and we can throw it open at the end to wildcard questions. Yeah. But let's see if we have any more EasyNeck SimSmith questions.
Okay. Well, the one I had is when you were looking at the 80-meter end-fed half-wave antenna.
Yep.
And I noticed that, on 80 meters, for instance, the SWR was pretty high and then it got lower at the upper bands and everything. Now, I guess the question is, let's just look at EasyNeck and put SimSmith to the side here. Just on EasyNeck, can you specify a 49-to-1 Valiant, or can you at least look at the impedance to see what impedance you're dealing with? So you know which type of winding you want to use. In other words, you can look at your 80-meter antenna again. You can look at the impedance there and say, well, what type of un do I need to step that impedance down to 50 ohms? Is that something you have to do on SimSmith, or can you specify an on EasyNet that will step that impedance down?
So you broke up a little bit there, Steve.
Okay.
So can you see I brought up the 80-meter end fed up at 24 feet. You guys see that?
Mm-hmm.
Yes.
Okay. So it's at 24 feet that you can see. And then I've also dropped a counterpoise from 24 feet down to 3 feet. So I've got a 21-foot counterpoise. Of course, I can change that any way I want to. So I don't want to bring it down to 0 because then it'll be grounded. And I didn't want to ground it. I wanted a floating counterpoise on this guy. So let's run the SWR real quick. Should run fairly fast. So Steve, can you rephrase your question?
Yeah, I guess when you look at the SWR, I guess the question is, I would think like what you want to look at is what is the impedance you're seeing on 80 meters? What's that feed point impedance? So that once you know that feed point impedance, then you can determine what type of unon you need to step that impedance down.
Okay.
I
So
thought, well, you
here
see,
we've got a here we've got a resonance at 3.5 megahertz. We got a resonance at 7.1.
yeah,
Got a resonance at 10.7. We got one at 14.3. And an oddball at 17.9 and 21.6. Not too shabby, right?
well, let's go back to 80 meters and let's look at that once again. Can we go back there? Yeah. No. Is there anything that shows the actual impedance? You know, like if
Oh,
we're near
sure.
resonance.
Yeah, sure. So here's what you do. It shows it to you down here, Steve. See the lower left-hand corner?
Yeah.
Okay. Frequency, SWR. Okay. And then the second line of the Z equals 185 and a plus 58 J ohms. So it's 185 ohms of radiation resistance. So that's why it's about almost 4 to 1, about 4 to 1 SWR.
Yeah, I guess I always thought like when you're running an end-fed half-wave antenna, you have like a voltage maximum and a current minimum at the feed point. So I thought the impedance was going to be about
Let's take a look
2,500
at
ohms.
let's take a look at that.
Yeah.
Let's take a look at the far field plot. All right. And you can see here, let's zoom in on this a little bit on the antenna. You see the let's move in the Y direction here. Yeah. Too far. Let me reset that. So there's the current plot in magenta. You see that, Steve?
Yeah.
You see the little green dots? Those are the ends of my segments.
Okay.
And you see I put a bunch in on the vertical, the counterpoise here. And you see
Yeah.
the magenta current curve for the counterpoise here.
Yeah.
And the
Well,
bubble is my feed point.
okay, but okay. I guess I always thought like when you're dealing with an end-fed half-wave antenna
Yeah.
at resonance, you know, the resonant point should be, the reactance should be something close to 0 ohms. Doesn't mean 0.00, obviously, but the resistant component should be about 2,500 ohms, I thought, on a
Well,
end-fed half-wave.
yeah. Well, it's interesting because you're right. One would expect a much higher impedance on that.
That's right.
So let's see here. We're getting about roughly 200 ohms impedance. Might be effect of the counterpoise. It's a particularly long counterpoise. But let's do something here. Let's run this into SimSmith, and let's see what we can get for a hang on. Let me bring up EasyNeck. This is how you get the last data, last Z right there. Nope, wrong one. Hold on a second. So, no, hold on a second. Oh, it's trying to load an EasyNeck file. No, the way to do that is to click on this, and then you click on EasyNeck, And in the EasyNet folder is that file right there. And then you say load. And now we've got the lassie loaded in here. We can close that window. See that? We got lassie. It's loaded in there. And we're starting way over here. Okay. So I have I had an on in my previous experiment before we fired up this meeting tonight. So let me bring that in the other direction. Notice this.
Mhm.
Remember, I've got a high impedance here, so I need more turns on this side than I am here. So this needs to be a partial tap. So this wire needs to be down here somewhere, right? Does it make sense?
Yes.
No.
Okay. So look over here what's happening on the green dotted line as I do this.
Bring her down.
Okay. And then, as we saw before in the video, I can do that. And if I really needed to, but I'm well within the 1.5 SWR, even without doing this, right?
Mhm.
So I can, so there I am, dead nuts on 1.01 SWR. And I want you to look at this. 1 watt in, 99% through the on, and then 99.7% into the antenna. So it's almost perfectly efficient, just with an on. So that's what I would do, and then I would measure it with a nano VNA and see how close EasyNet got me. And then the other thing we could do is, if we wanted to, we could change the length of this counterpoise here, and we'll make it, what is 5% of that? So it's about 6 feet. So it'll go down to 18 from an elevation of 24 down to an elevation of 18 feet. So now this little counterpoise is just a little tiny stub, and I can rerun the SWR and see what we get. So, Steve, again, don't use EasyNet as gospel. Use it as a guideline, right? Use it as a guideline for kind of like hot and cold, right? It's the hot and cold game. You're getting hotter, getting colder. Think of it that way. And then measure it with the nano VNA and then see what you get. So here it says always reload, and you always want to take the reload because then it'll actually always reload that. And now, interestingly enough, let's see, let's get the scan here. So that's the new scan. See the difference it made with the short counterpoise? That counterpoise can make a huge difference. All right, so at 3.8 megahertz, changes our frequency for 80 meters, and it's the Z is down at 11.5. Interesting. Hold on a second. I mean, I want to go over on SimSmith and 3.8 megahertz. No, it's why is SimSmith reporting something different on the impedance? Because right here, I'm at 3.8 megahertz is my analysis frequency. That should be telling me what kind of impedance I'm getting, almost 600 ohms, which would make more sense. Oh, hold on a second. Well, no, that's the natural impedance coming right out of the antenna. That's before any messing around with the on. Let's see what we got going on.
Seems like it should be a lot higher though, shouldn't it? I mean, I realize like end-fed half-wave antennas, that feed point impedance can vary a lot, but the whole idea is, can EasyNet tell you, do you need a 49-to-1? Do you need a different ratio? So
well, let's try it, right? It will get you into the ballpark.
Well, yeah, I guess I'm more concerned about EasyNet than I am SimSmith right now. I'm just saying, can the EasyNet tell us, once we specify the antenna we're using, what type of feed point impedance we're going to be looking at, approximately, of course. It's not perfect, obviously, but
Okay, so here's a classic example of an unknown. And it's a 54-to-1 ratio because these are actually inductance values in microhenries. So that would be the ratio, 54 to approximately 1, a little less than 54, which is pretty close to 49-to-1. That's what it wants to satisfy it. And it wants a little capacitor of about 1 nanofarad,
yeah,
1,000 picofarad,
yeah.
to bring that down well within the 1.5 SWR circle here. And you guys all know how this all works, right? You've seen SimSmith, so you know what you're looking at. So this is the green capacitor, and the magenta line, dotted line, is the anon. So you can see that most of the coils are on the antenna side since it's a high impedance, and a small few taps on the input primary side. So again, like I said, you have to take this with a bit of a grain of salt. These are kind of guidelines. And if you really get into EasyNet and really get into the setting, all the settings perfectly on a fairly straightforward antenna, you can get a pretty good matchup between EasyNet and a Nano VNA. But when it comes to anything having to do with grounds, you could get yourself off quite a bit because EasyNet makes certain assumptions about grounds that you may not be taking into account. But you can see how this has changed the resonances quite a bit. And so here's my analysis point. You can see the bubble down here. That's telling me that I'm up here at 3.8 megahertz. And so within the bubble, I'm getting, well, you can see it's extremely sharp at 80 meters. Very, very sharp. It's just a few hertz, maybe a couple hundred hertz wide, if that. But it gets wider and wider if you're out here. Let's take a look. If you're in here, you're probably at, okay, 8 megahertz. So this you'd want to dial in for the 40-meter band. Okay. So anyway, end-fed half waves are kind of a little bit of a black art in terms of setting up and getting everything dialed. I'll tell you one thing about end-fed half waves. They really, really don't want to be close to the ground or close to metal. They want to be up in the air all by themselves. I'll tell you why. I'll show you something really interesting. Let's go to the analysis frequency here up high at 28.4. Okay. And then I'm going to run the far field plot. I want you to take a look. Look at the waves on this end-fed half wave, the number of waves you get on there, the current waves. Okay. And look at the complexity of the radiation pattern. It gets kind of hairy. Yeah, you get some pretty good sized lobes at a low angle, but you got a lot of energy for NVIS going up there. That's for sure. So you know what? If you want to do NVIS, this is maybe not a half bad antenna. So any other questions? Any other games you want to play?
Well, one last question. Not that we could try doing this, but I know like where you're at home, you have a fan inverted V or fan dipole where you have like, I don't know, 20, 15, and 10. So I guess with EasyNet, you could set that up so that you have those three antennas, separated too, not going all in line and everything. But have you ever tried that on EasyNet to see?
Nope, but it's pretty easy.
Okay.
Well, let's see. I was using that with a ground radial with a whole bunch of the silicone wire ground radials, and I could build the vertical fan basically a half a fan dipole in 3 dimensions But then it would take me a while to build the ground radials. What I would do is I'd build full length wires through the middle of the base and have enough segments, odd number of segments, so that I could get the feed point right there.
Yeah. Well, what I was talking about was, rather than that, 3 inverted V's. We're not talking about verticals now. We're talking about 3 inverted V's, all with a common insulator.
A classic inverted V, a classic multi-band inverted V's.
Yeah.
Separated by angle.
Yeah.
Okay.
So you
that's
before
pretty
you
easy.
put yours up at home, you did this on EasyNet to see, what type of dimensions you needed and everything like that.
Okay, let's do that. What height do you want it at? At the apex?
Well, if it's 20 meters, let's say 32 feet. And then I don't know if you can specify.
So we're gonna put this guy. Hang on a second.
We got 3 wires now, of course, not just 3 different inverted V's.
So I'm gonna go. I don't remember the length here. Well, what I would do, you could. I don't know if we have enough time in this video online to do this, Steve, but
no, I didn't want you to do it. I was just wondering, like when you did yours at home,
absolutely,
did you use EasyNet to figure this out?
You can absolutely do it. What you do is you've got to figure out. You see my little 3-dimensional diagram here in the upper right?
Yeah.
Okay. What you would do is you'd have a wire starting not near the ground, at least 6 feet up, going up to the apex. That's one wire, okay, with a number of segments. Then I'd have another wire coming down in the same plane, in this plane right here, the YZ plane, okay? And then I'd have one coming down the other side. Then you could have one coming up here in this plane, in sort of halfway between Y and Z up to the top, and then down, and then another one over this way, up and then down. And then, so you could do like a 3-bander, 20, 15, and 10. And the elements would be up high, which is good, where you get your current high. And the bottoms would be off the ground, which is what you want, at least 6 feet. And the other thing is you want to have an apex angle of no less than 120 degrees. I find 90 degrees is a compromise. I really like to see more than at least 120 degrees, which means you need to get that poly cord, guy wire end of each one of these things out there quite a ways away from the push-up mast.
Yeah. Okay.
Does that
I
make
knew
sense?
that's what you had at home. So I was just wondering, before you put that antenna up at home, did you do the EasyNet thing to get some ideas of what you have to use?
I was comfortable enough to just put the antenna up and it worked.
Okay.
So
okay, great.
It's about as almost as classic dipole as a straight flat dipole, right? So I didn't really bother modeling that one, but I could, but you could too. I mean, use that as a great starting point. It's not that hard to build.
Yeah, that's what I think I'll do. So.
The thing it's probably a little bit at first a little daunting, but once you get it, it's not that hard, is the geometry of the system, right? This is Y, this is X, and this is the verticals. This is Z, vertical. And you have to put the coordinates of each endpoint of each line, not a segment. Here I've got segments, but we'll call it an element, okay? The X, Y, and Z of the one end of the element, a wire, right? And the other end of the wire. And you're building out of individual wires that you're hooking together, and then you put a source in there. Okay, that's all there's to it. And then you can run an SWR.
Yeah, interesting. Okay, thank you, Ruth. Okay, that's all I got.
Okay, questions? David, we haven't heard from you. There must have been something in the video that was still fuzzy to you.
Well, I'm catching on. It's pretty slow, but I see where you're going, and I see how these all connect. Rather than asking a question that may be unintelligible, do you want to show, Kitty, just a minute. Do you want to show the antenna that we talked about with the 4 radials?
Oh, sure. Well, that actually was in the video. Let me open that up. And
yeah, I saw that you brought it up, so I was hoping to see it again and learn a little bit more about that.
you betcha. So let's see. This one was called with short elevated radials. You can see I've got like hundreds of different models in here.
These are these ones that you have modeled, or are these
Mostly.
samples?
Mostly.
Okay.
Okay. 20-meter vertical with short. Oh, that's a spiral. Hang on a second. Short droop radial at 20 feet up.
Sounds about right.
I think that's the one. Yep. So
Yep,
we
kind of
got
looks
a
like it.
yep, we got a long element there. Notice at the feed point base of the antenna itself is at 20 feet, and the tippy top is at 41 feet, 21-foot long whip. Why? Because my radials are short. They're only 4 feet long. You can see that these are 2.8 feet out and down by 2.8 feet. So 2.8 feet is about 4 feet divided by 1.414, which is a radical square root of 2 for a 45-degree angle. So I know that these guys are at a nice 45-degree angle. So
and then you said your element was 20 feet long, but
take a look at 21. Just
21.
subtract 20 feet from 41 feet.
Okay.
The
But
tip
I've
is
got
21 and the base is 20 feet on the whip.
got a limit of 17 because that's as far as it extends.
Right. And so let's do that. Let's first, I'm almost done with the SWR scan right now. Right now. Okay, so that's what it looks like with a 21-foot whip, which we don't have, right?
Right.
And even that is still not long enough because it's at 15.5 megahertz. Okay, it's 1.2, but it's not resonant at 20 meters.
Mm-hmm.
It's short. So what do? Well, we can either lengthen it or we have to do some other Sim-Smith trick, right? So let's do that. Let's take it to 18.5 feet, which would be 38.5 feet. Okay, so there's our real 18.5-foot whip above 20 feet. Okay, and now I have to, yeah, this is still the same because I'm working off the base of 20 feet. So everything else is the same. And let's see what we get now. While it's doing that, I'm going to trash those things. And so getting close here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bingo. All right. So now you can see that we've got is up at 17.2, as you would expect. All right. So what do? Put a bloody tuner in there. And let's tune it up for 40 meters. Excuse me, 20 meters. See what we get. And there it is. And let's take a look at our Sim-Smith to see what kind of bandwidth we're getting. All right. So on this locus, so I can get it below 3.0 across all of the 20-meter band. And by the way, I can tell you that EasyNet can be kind of conservative. In real life, if you get an antenna in the kill zone, it actually sometimes turns out to be better than EasyNet predicts. So just think EasyNet is going to be on the conservative side. I found that this antenna that I built, because I built one, I've got one in the backyard. You heard me on the Thunderbird net. I said, this is the antenna I talked on the Thunderbird net on Sunday night, guys. this exact antenna, 18.5-foot whip with a common mode chick at the base, the auto tuner, remote auto tuner at the base, and this is what I got. And so let's take a look at 28.42. And that's the analysis, and I have to also auto tune it to 28.42. And now let's take a look at the Smith chart, and let's take a look at the bandwidth there. All right, not bad. 2809 to 2864. I'm well within 1.5 SWR. So I've got this nice long area of frequency that I'm within my 1.5 SWR circle on this antenna. So let's do another thing. Let's take a look at the far field plot. Okay, I got to change the plot type back to 3-dimensional. All right, you can see the magenta current, and you can see, although I have somewhat of a skywave, I've also got a very, very strong horizontal, which makes this a very good round town point-to-point antenna, actually. Let's do something. Let's change the plot type to elevation so you can get some actual numbers here. All right, so there's my skywave lobes, but I've got a very nice strong lobe at 13 degrees above the horizontal with a gain of 1.1, which is not the greatest, but it's not bad, especially for a multi-band antenna. That is overly long for the band, because 18 feet is okay for a 20-meter vertical, but not so much. You'd want something like 8.5, 8.25 feet for 10-meter vertical. Half that, of course, right? 20 meters, 10 meters. But even so, we're getting a very nice, with the tuner, we're getting some pretty good results. So, questions?
Yeah,
And look,
Rudy,
go ahead.
is there any advantage to varying the ratio of the radiating vertical element and the length of the radials? Radials, like you
Yes.
you could have really short radials.
Yes, there is, Ron. There absolutely is. You absolutely want to try to make the radials approximately equal to the length of your longest wavelength. Okay. And it's really the amount of surface area that you're covering. Okay. And if they are approximately the same as your vertical, and your vertical is at resonance, so for 20 meters, it would be about 18.5 feet. If your vertical is at resonance and the length of all your radial wires are around 18.5 feet, and you got a bunch of them down there, you've got a very balanced system, okay? And that means that your native SWR, and that means, let's see if I can find that plot. Hold on a second. It should remember the last SWR plot. There it is. That the native SWR is going to be very nice. Now, notice that the native SWR here is resonating at 17.3 megahertz, but that's because this element is really, really long. Not because the radials are short, but the main radiating element is really long. And even so, with a tuner, I was able to get this sucker up. Let's take a look. Oh, hang on a second. I just noticed something. I did not put EasyNeck into 10 meters. Let's do that. Let's run the far field plot again now. All right, that's a little bit different. So I am getting a some decent energy at a low angle down here at 11 degrees, but 10, 11 degrees. But I'm not getting the kind of, not quite at 20 meters. At 20 meters, it makes a really, really good local antenna, really low launch angle, actually a fairly decent DX antenna. All right, so that's what this looks like in 3 dimensions. Looks like a bundt cake. So anyway, more questions?
Well, we filled up the hour pretty well there, Rudy. I noticed that we had a late gentleman come in, N7ZEV, Frank Kostelak. Hey, Frank, how you doing?
Oh, hey, Frank, nice to see you join.
Yeah,
you wanna-
just good evening. Thank you.
I talked to Frank the other day. He left me a voicemail that I was cleaning up and I never got back to him, and I finally got him. So I'm glad you could join us, Frank. Frank, before we leave, do you have any questions or comments? Did you watch video 6, by the way?
I did not. I was just, that's why I arrived late. I was running late.
Ah, okay. Well, then some of this may not make that much sense to you, but
Oh, it all made sense. We're good.
okay, cool. So, Frank, do you have any questions or comments before we wrap?
No, thanks for the invite.
All right, very good. Anybody else? Last call.
I think we've got it, Rudy. That sounds
All
good to
right.
me. So, on that note, what is our next podcast you're coming up with the end of this month?
I'm working on diversity mode and SDR.
SDR. Okay.
SDR and diversity mode receiving.
Oh, excellent. So you're going to use the 30M or
MLA
Excellent.
30 plus. The
that
loop.
sounds like a lot of fun. That should be a very good one. And of course, I believe that we are the next one is on February 7th, or I mean August 7th.
August
So,
7th.
and I'll send out the blast about that around the 1st of August. So everybody have a great 4th of July tomorrow. Don't light up your antennas. Okay. Keep the power down. There's enough fireworks going on. We don't need to do that. So everybody have a great week, and catch you all the next time. Thank you, Rudy.
Thanks, Rudy.
Thank you, Rudy.
Yeah, 73
job.
all.
Thank you.
Thanks,
Bye-bye.
Rudy. Thanks, Rudy.